Alright, we are starting the chapter on cams now, and because I'm going to follow the textbook, I'm just going to take a few pages from there. Please notice that much of the chapter is not included. Okay, so there is a classification of cams. There is the radial translating follower, offset translating follower, oscillating follower. There can be a knife edge, flat face, roller follower, and a spherical face follower also. Let's scroll down to the next page in the book, and you see this is the knife edge one, this is the flat face one, this one has an offset. You see this line and this line are different. There's an offset. This one has an offset also. You may think that this offset has no real meaning from the kinematics point of view. That is true. But in terms of how forces are transmitted, for example, if the force was here, then its tendency to lock due to friction will depend on how much the physical offset is. So you may want to pay attention to that when you're designing a cam like this. This part is the cam. You can see there is a keyed shaft in here, so this will turn the cam like this, and the follower will go up or down. There will be some spring keeping this follower pushed in that direction and maintaining contact. That is usually not shown. So here is the other cam now. This one is a flat-faced follower with an offset. Here is a roller follower. This is an oscillating follower. This one is a wedge cam. So this one just moves like this, and it moves the follower up or down. This is one type of cylindrical cam. So you can see this is the cylinder. It rotates about this axis here. This is the follower. It is hinged here, and this part is in a groove. This picture is not very clear, but you can think of the cylinder as having a groove that runs along its curved side. So as the cylinder rotates, this oscillating follower oscillates back and forth. You come here. This is also a little difficult to understand. This is a cam where your follower is moving on the the axial side, the front face of the cylinder. These are two cam designs which you can see that the center is a bit offset, right? So this will move, this cage will move. These are designs where springs are not needed. So there is actually contact from two sides. So this over here comes. You can see that it is attached over here with the weld and hinged. So this will follow, and that is the cam. Okay. So now these are some cams that are there just for your background knowledge. Now let us move to radial cam nomenclature, some terms. These are the terms here. So what I will do is let me begin with blue. So here is the follower. This is a radial cam. That means this path, the eccentricity is 0. This path, that line passes through the center. Okay, now where is the cam? This curve here, that's the cam. That's the cam profile. There is the shortest distance, and that gives this circle here, which is called the base circle. I think I can help a little by making it bigger. Now there is another circle. This is the base circle. This is the cam. Now this here is the follower. It's a roller follower. So it always has a certain distance from the cam profile. And so it actually follows relative to the cam. If you think of kinematic inversion, it follows a different path. Okay, so there are names for that. The cam rotates either this way or that way. There are some names for that. So here is the base circle. That is the smallest circle that you can fit, whose center is at the center of the axis of rotation of the cam and which is tangent to the surface of the cam. Now there is a prime circle, which is basically the slightly bigger circle defined by the roller radius and the base circle radius. Okay, there is the pitch curve, which is this entire curve, which we obtain, as I explained, by kinematic inversion. Right, so all of these things are defined here. You can look at them in the book. There is the trace point. The trace point is the point on the follower which we keep track of to see how the follower is moving, and the pitch curve is determined by the locus of the trace point relative to the cam. Over here is something we will be interested in, which is the pressure angle. The pressure angle is the angle between the radial line. Why radial line? Because that is the direction of the motion of this. It's a radial cam, and the normal to the pitch curve. Okay, so these are there's the pitch circle passes through the pitch point, which is the point where the pressure angle is largest. Okay, so these are some terms that are used. Now the next pages in the book are description of follower movement. They talk about, this, when this one moves or when this one moves, there is a displacement y that it takes, and that y as a function of theta is what they are talking about. And they will have a lift, and they'll have a dwell, and they'll have a return, and they'll have another dwell. This is very common for cams. So if you have a graph of y versus theta from 0 to 2 pi, you'll have a dwell, a lift, a dwell, a return, and a dwell, something like this. Okay, you can see that part, but we will not spend much time on it. So now we will come to section 8.6, which is determination of basic dimensions of a cam. Now this is a part that is actually quite surprising. So based on some relatively simple information about what the desired y is, and whether it is a flat-faced follower or some other rather remarkable conclusions can be drawn. Okay, so let me show you now. Let me see if I can make it a bit bigger. Now here, this is the base circle. This is the cam profile. When this part was here, then the follower would be here. You see, so y is measured from here. That's why y is measured from here, and that is why this is the radius of the base circle. But this is later at some arbitrary time. This is the contact point now. At the contact point, there is a radius of curvature. That circle has a center somewhere, and as has been discussed and used a couple of times in the course so far, what happens is up to 2 derivatives we can think of that circle as constant and the center of the circle as constant. The center of the circle is located at some point relative to this, so we can locate this using some line. And the other thing is that the cam has rotated. Theta is measured as 0 at the point where lift just begins. So this angle is theta. What is interesting and what you need to understand is that for up to 2 derivatives, theta plus psi is constant, because this point is fixed in the cam and this line is also fixed in the cam. Okay, the cam rotates as indicated over here. This will move. It moves with a certain velocity. That's fine. Over here is the eccentricity and the offset E, and then there is the eccentricity epsilon, which varies with time. The offset E is fixed for a given cam design. Okay, so now as I indicated, this theta plus this phi, this is a constant for up to 2 derivatives, and that gives us this equation here. This one, now I think I will have to make it smaller, otherwise we will not be able to follow. Now you see rho, RB, Y and OC cos psi. So let's come here. This is the radius, this much, this is rho, and that is equal to RB plus Y plus this distance. And what this distance is OC times the cosine of this, which is cosine of pi minus psi. So over here plus OC cosine pi minus psi, that becomes minus. Okay. Now we can differentiate that one, and then we obtain this equation here, and as we know, this will be used to simplify that. With that simplification, we have this expression. We can differentiate once more. As we said, we can take 2 derivatives, and when we do that, there is a theta prime here, or a d psi d theta here, or however we look at it, and then we get this expression here, and this leads what to me is a rather surprising expression. Okay, so this OC cosine phi is what was needed. You see, we differentiated here. You come here and you look that OC cosine phi was in this expression, so then it becomes y double prime. That is why it is surprising to me, but rather beautiful. Here, this is what we have. So now you see on the cam, if your cam profile is like this, that means rho is very small at that point, right? In that case, the contact stresses may be very large. You may not like to allow that. So if rho minimum is the minimum permitted, then what happens is, you see, you write it like this. You see, RB is a design parameter in the lab, for the can. RB is something you need to choose, the base circle radius. Rho min is determined from the contact stress point of view. Someone says let the local radius of curvature of the cam profile not be smaller than this. So when you do this, we end up here. You see, what happens is rho minus y double prime. Now the question is, this is an equality, right? I mean, this is always true. So if you take its minimum value, the minimum value of this, right, is equal to, the minimum value of this, and then minus whatever that is. So in this way, you can find out how much this has to be. Okay. Now, when someone gives you y as a function of theta, then you can take your derivatives, and from that you will find what is going on. Okay. Now the eccentricity of the driving effort, as we spoke about this is the eccentricity, this one. So this eccentricity, we don't want it to be too big. So OC sine psi, we will come here, you see, this is OC, that angle is psi. So this is OC sine psi, that is L, that is E plus epsilon. So OC sine psi is E plus epsilon, and then sine psi is y prime. You see, OC sine psi is y prime. So we come back here and we get this expression. Okay. So depending on how much this is and how big you are allowed, how much the maximum value of this is that you have wished to allow, you will have to choose this. One of the things you have to understand is that these restrictions apply only on the rising part of the curve. When this cam is turning like this and pushing this one up, that is when we care about it. When the cam has turned so much that the contact is on this side here and it is coming down, then the spring brings it down and we don't bother about it. So we are interested in the rising part, and using the rising part we are able to find out what the minimum has to be. Okay, so this is how big we will allow it to be. This is the rising part and this is the maximum slope, and that tells us how much the eccentricity, the offset, the minimum value of the offset has to be. Now finally we can also calculate, this is more trivial, what is the width of the cam face that we will need. So that is, there are two sides to this, rising part, falling part, both times contact has to be maintained, so that gives us two terms there, and then some allowance we can keep. Okay, this we are not looking at. So that's a flat faced follower. And now we will move to something where we approach in a different way. So this is the roller follower. Here also there is an offset. You will notice this is the offset, that is E. Let me make the picture a bit bigger so that you will see it a bit clearly. This picture is a little less clear, but I hope you can see what is going on. And now, once again, this is the base circle over here. This whole thing is the cam profile. This is the pitch curve. This is the roller radius. This is the follower. Where does this begin? So when the cam is on this side, let me draw it with yellow or something, so that you see when the cam is on this side. I shouldn't have done that. I don't know if I can remove it. When the cam is on this side, this roller will come down and it will be sitting on the base circle here. You see, so that is where y is measured from. That is why y is measured from here. Okay, and how much is this height? This height is determined in terms of the pitch circle radius as well as the offset. See, because this is the pitch circle radius and this is the offset, and so this height is given like that. This thing has a center. That center is here. So that point is C. So we think of C as rigidly attached to this cam. We think of O as rigidly attached to the cam. We think of this point S, which is the point that was here. Okay, when this was at the lowermost position. So that angle is theta. This angle is psi. And for up to two derivatives, theta plus psi is constant. Okay, so now here, we have the radius of the pitch circle, radius of the roller. We don't want the cam profile radius to be too small. We may have all of these constraints, but let us see how our sizing proceeds. Okay, so something very clever happens here as well. Let us write ON as OA sin phi and AP cos phi. Let me explain. So here let me use red. This is ON. This is the perpendicular direction. So this angle being phi, this angle is also phi. And so we can reach this same horizontal extent, ON, by traveling from here and then coming like this. And so we have OA sin phi plus AP cos phi, but AP is E. That is why we have OA sin phi plus AP cos phi. Now what's OA? OA is equal to this height plus y, and this height is, as we know, here. That is why we have this height plus y sin phi plus E cos phi. This is ON. That's our first observation. The other observation is component of velocity of point P along CP. Okay, so we come here, this line from C to P. Now, the component of the velocity of P along CP has to be what? That is what we want to know. So this velocity, its actual velocity is upwards, it is V. That cos phi is the component in this direction, and that has to be equal to omega times On, because this is a rigid mechanism. If you think about the kinematics, you will see that happens. So that is why we have omega On is equal to dy dt cos phi, or V cos phi. Okay. Now theta dot is equal to omega, and that gives us, basically you see, y prime of theta into d theta dt. So that is omega. So we have this expression here. Okay. Now On we are substituting. Again, On is what we have just found here. Remember, this is On. So when we substitute for On over here, we are able to solve for tan phi. And to me, again, this is a remarkable formula, because it can be expressed in this picture. Let me make it a bit smaller so that we see both. So you see, you have a desired y, which is a function of theta, and you also have a dy d theta, which is plotted in this direction, as it happens. So you have dy d theta in this direction, and then y versus y prime is a closed curve. Okay. Now remember that in the displacement curve, there was a dwell and then a rise and then a dwell and then a return and so on. So there was a place where y was 0 and y prime was 0. There was a place where y was maximum and y prime was 0. This is the place where y is 0 and y prime is 0. So this whole dwell is just here. This whole dwell is just here. Okay. But the rising part is here and the falling part is here. Now over here, how do you know the arrow is like this? That is because y prime is positive. That means y is increasing. So this is the direction in which it moves. Now we come here, what we do is we come to the left by an amount equal to the offset, and we draw this line equal to RP, or its circle radius, in length. And then what happens is, you see over here, because this distance is E, what is this distance? This is some typical point on this curve. What is this distance? This distance is y prime minus E, that is the numerator. And what is this distance? That is equal to y plus this distance, which is here. And therefore you see this angle is the pressure angle. So that angle is tan phi. Now this is very interesting, because RP and E are design parameters. Y and y prime are, specifications that the CAM designer will receive. Okay. So now that is what they are showing, that is tan phi. When we come to the next page, okay, the radius of curvature of the CAM profile can also be found. So the radius of curvature, what is done is, we go to figure 8.10 and we write this again. So let us go and see what is happening. this whole thing from here to here is the radius of curvature, well, of the pitch circle, and that is equal to three things. So let us see what it is. It is equal rho p cos phi. So we write it directly, this angle is phi, rho p cos phi is this vertical height, that is equal to y plus this quantity here, and then we need something here which we will get as, I'm sorry, this part here, we will get it soon. It is this vertical part which is OC cos phi. Why is that? Oh, it's simple. This vertical part is OC cos of pi minus psi, therefore minus OC cos phi. Okay, so and then let's see, there is the sin phi also. We come here, rho c, this one PC or rho p sin phi is equal to this distance here, right, which is OC sin psi minus E. So we come here, that's what it is. And then when we differentiate with respect to theta, then the sine becomes cosine, and then on this side E is a constant, this psi becomes cosine psi, okay, and then we have d psi by d theta is minus 1. Okay, why? Because psi plus theta constant up to two derivatives. Okay, so that's minus 1. So we have this expression. This we solve for OC. OC cos phi is what we need. When we substitute, then we get this expression, which we solve for rho p. This thing is all good, except it has a phi and a phi prime. Now we don't actually have cos phi. What we have is tan phi. That has to be changed to cos phi. Then it has to be differentiated, and so on. And when we do that, we get a bit of a nasty expression, which you just should read from the book. Okay, so then after that, this expression can be used to make sure that the cam does not get a cusp or something. Because you see, when you calculate this one, then you have to subtract the roller radius to find the radius of the actual profile. Okay, and then finally I will show you one problem where they said here is the displacement profile needed. So here is y and here is y prime, and they don't want, in the rising part of the motion, they don't want the pressure angle to be more than 30 degrees. So that means both sides, right? So there, suppose the cam is like this and the follower is like this. This is one situation, and later the cam may be like this, and maybe like this, and the follower may at that point be like this. So here the pressure angle, if that is positive, then over here the pressure angle will be negative. So both must be allowed. Now in the rising part of the curve only. So over here we are not interested in these points. This is the beginning of the rising part of the curve. This angle 60 degrees means this is 30 degrees. That's the pressure angle. So we draw a 30 degree line from here, and we draw another 30 degree tangent from here, and it intersects somewhere. Now the point is, if I am somewhere here, then I will get a larger pressure angle than 30 degrees. So to have I can't be here because I'll have a larger pressure angle, right? So I have to be to this side of the line, I have to be to this side of the line, and the smallest radius possible then is this value here. And that tells me, in this case for this geometry it was 18, but it tells you what RP is and what the offset is also. Okay, and now if the roller radius is given, then you can find the radius of the cam profile. Okay, now if phi max is greater than 45 degrees, greater than equal to 45 degrees, then you should not draw this line, you should draw a perpendicular. It is mentioned in the book. It is not difficult to figure out. I will leave you to think about it. Okay, so in the next lecture we will use analytical methods to find cam profiles. The graphical methods of cam profiles we will not do. Thank you.